we will now discuss the third episode of ethers and epoxides. In the earlier episode, we have discussed the physical and chemical properties of ethers. In this particular episode, we are going to introduce a new class of ethers called epoxides. Epoxides actually are cyclic ethers. In this episode, we will discuss the introduction, nomenclature, preparation and reactions of epoxides. First of all, we will discuss the introduction of epoxides, then nomenclature, their preparation, and the epoxides can be prepared from alkenes, they can also be prepared from diols, they can be prepared from halohydrins also. We will then discuss the reactions of epoxides and the main important reactions of cyclic ethers, that is epoxide is base catalyzed and acid catalyzed ring opening reactions. They also show some reactions with organometallic compounds. So, first of all, we will discuss here the structure of epoxides. Epoxides are ethers which have oxygen atom in a three-membered cyclic ring. You can see here that this epoxide has a three-membered ring, 2 carbons and 1 oxygen. Now, if you recollect, a three-membered carbocyclic ring is highly strained ring according to Beer-Stein theory also and according to Sasser-Mohr theory also. The reason is that all the atoms, whether it is oxygen or carbon here, they are all sp3 hybridized, and with sp3 hybridization, the normal bond angle between any 3 atoms should be 109.5, whereas here you can see the angle is about 62 degrees, that is the ring is highly strained, and this kind of structure, this oxyrane structure or cyclic ether structure has a lot of strain on it, and because of which it shows a number of different properties. The carbon oxygen carbon bond angle for an epoxide must be 60 degrees, which is a considerable deviation from the normal tetrahedral angle of 109.5. Thus, the epoxides have large angle strain and which make them more reactive than other open chain ethers. We will now discuss the nomenclature of epoxides. The epoxides can be named as epoxy alkanes, they can also be named as oxyranes, or they can be named as alkene oxide. We will discuss all the 3 methods of nomenclature of epoxy alkanes one by one. First of all, nomenclature as epoxy alkane. In this method, the first we have to name the alkanes chain or alkane ring to which the oxygen atom is attached, and then a prefixed epoxy is used to name the epoxide. The numbers also are designated before the name just to show the location of atoms to which the oxygen is bonded. You can see with the help of this example here, the simplest one here is this one, where you can see the carbon chain comprised of 3 carbon atom 1, 2 and 3. At position 2 we have a methyl group and 1 and 2 is attached to oxygen. So, the name of the molecule will be 1,2-epoxy 2-methyl propane. Similarly, here in this case you can see that the maximum number of carbon in a chain are 5, 1, 2, 3, 4 and 5, and position 2 and 3 is occupied or attached to oxygen, and that is why the name given is 2,3-epoxy pentane. But here we can see that a cis is also given over here. If you recollect, cyclic molecules show cis and trans isomerism depending upon the substitution. If the substitutions are on one side of the molecule, then they are called cis, and when they are preferential groups are on both sides or opposite sides I would say, then they show trans isomerism. So, here this molecule is a cis 2,3-epoxy pentane. In this particular case, this is a cyclohexane ring and position 1 and 2 of cyclohexane is attached to oxygen. That is why the name given is 1,2-epoxy cyclohexane to the molecule. We will now discuss the second nomenclature of these cyclic ethers as oxyranes. The epoxide, actually oxyrane is the name of the three-membered ring. Oxygen as one of the member of the three-membered ring. Position 1 is given to oxygen always, and 2 and 3 is the position of next two carbons. Now, if in this particular case you can see that if this carbon is attached to methyl group, two methyl groups are attached over here. So, the name given to this molecule will be 2,2-dimethyl oxyrane. Oxyrane is the name of the molecule which is unsubstituted, where there is no substitution on any of the two carbons. But if there is substitution on one of the two carbons, preferentially that carbon is given lower number. We cannot number the molecule like 1, 2 and 3. We will have to number it in such a way that minimum number goes to substitution, and that is why the name of the molecule will be 2,2-dimethyl oxyrane. Now, the third method to name the molecule, these cyclic ethers, as alkene oxide. In this particular method, there are three steps. First is mentally replace the epoxide oxygen with a double bond. Then in the second step, we name the alkene, and in the third step, the word oxide is added to that name. We will discuss it with the help of this example. Here you can see that this ether, cyclic ether, is basically, if we delete oxygen or if we mentally think that there is no oxygen, then this is a 2-carbon alkene, and the name of 2-carbon alkene is ethene, to which oxygen is attached, and that is why we name this molecule as ethylene oxide. We will now discuss the preparation of epoxide from halohydrins. Halohydrins actually are the molecules which have a halogen atom and a hydroxide also in the same molecule. When intramolecular Williamson's ether synthesis takes place on halohydrin, then there is formation of epoxide. We will take you back to Williamson ether synthesis, which we discussed in first episode, in which we discussed that when we have to prepare unsymmetrical ethers, we prepare them by taking the sodium salt of any alcohol along with alkyl halide. Now, here you can see that in this halohydrin, one part of the molecule has alcoholic group and the other part of the molecule has a halogen atom. So, when we are saying that this is intramolecular version of Williamson ether synthesis, means one part of the molecule is giving us this alkoxide moiety and the other part of the molecule has this halogen. So, what happens here is that this hydrogen attached to this oxygen is abstracted by base here. So, base abstracts this hydrogen and there is formation of alkoxide. This alkoxide then attacks the electron deficient carbon. Why this carbon is electron deficient? Because it is attached to more electronegative halogen. As a result, this carbon halogen bond is a polar bond and is attacked by the alkoxide and there is formation of this oxyrane. We will now discuss the preparation of 1,2-epoxy 2-methyl propane from 1-bromo 2-methyl 2-propanol. You can see here it is 1-bromo and 2-methyl 2-propanol. At position 2 we have a hydroxy group, at position 1 we have a bromo group. So, here first there is formation of alkoxide by abstraction of proton. Second step is the attack of negatively charged oxygen or you can say alkoxide on electron deficient carbon, and there is formation of 1,2-epoxy 2-methyl propane. The preparation of epoxide by intramolecular nucleophilic substitution is shown in some of the examples which we are going to discuss further. But in this particular case, you will see that the molecule is the same. This molecule here, this has a hydroxy group on one carbon and a bromo group on another carbon. We are showing here the sawhorse projection of the molecule, and what happens here is that there is internal rotation along this carbon-carbon bond in such a way that the two groups, the attacking group and leaving group, they go in the anti-position. Anti-position means a position which is at a maximum distance from each other. As a result, you can see here there is internal rotation, formation of this another conformer where the two groups are at anti-position, and then attack of alkoxide on carbon and removal of bromide. In this particular situation, actually we are discussing the same molecule, but it is represented in Newman projection. The earlier one was Sawhorse and this is the Newman projection. Here again you can see that this is the alkoxide oxygen and this is bromide. They are next to each other. Internal rotation of the carbon-carbon bond brings the bromide and hydroxide at anti-position, and then there is attack of alkoxide on carbon and removal of bromide to generate this oxyrane. We will now discuss the preparation of epoxides from alkenes. Alkenes, when treated upon with peroxy acid, they form epoxide. In this particular reaction, this is a one-step process in which peroxy acid transfers oxygen to alkene with syn stereochemistry, and there is no formation of intermediate. Now, what is the meaning of this syn stereochemistry? Syn stereochemistry actually means that the addition takes place from only one side of the molecule. Now, why this addition will take place on one side of molecule? The reason is that alkene has planar geometry. Carbon-carbon double bond, both the carbons are sp2 hybridized, that is why it has a planar geometry. And as a result, what happens is that this oxygen from peroxy acid attacks from one side of carbon-carbon double bond. As a result, there is syn stereochemistry incurred into epoxide. We will now discuss the properties of epoxides, but before discussing the properties, we will have to recall that epoxides do not contain a good leaving group, but epoxide undergo a certain reactions. The reason behind it is that they do contain a strained three-membered ring with two polar bonds. That is why nucleophilic attack opens the strained three-membered ring, making it a favorable process even with a poor leaving group. You can see here that in this epoxide there is no good leaving group, but even then ring opening is taking place. The driving force for ring opening is not a good leaving group, but the strain on the three-membered ring. When epoxides are treated upon with strong nucleophiles or with strong acids like HZ, where Z is a nucleophilic atom, they undergo this ring opening. Unsymmetrical epoxides open differently in acid solution as well as in basic solution. Here this is an epoxide treated with cyanide, which is a strong base, and there is formation of this product, ring opening takes place. Here instead of cyanide, if we take HCl, then also the ring opening is taking place. The only difference is that instead of cyanide we have a chloro group here. So, this is both the examples are of the attack of nucleophile on the carbon of this oxyrane or epoxide ring. As a result, there is ring opening. Now, we will discuss the ring opening of epoxides in basic medium in detail. Here you can see this is a nucleophile which is a basic attacking reagent obviously. So, it attacks one of the two carbons here, and then in the second step hydrogen is abstracted from water. As a result, we get an addition product as a result of ring opening. In step 1, the nucleophile attacks an electron deficient carbon. See why we are saying that this is an electron deficient carbon? Because this carbon, both of these carbons are attached to electronegative oxygen. So, these are carbon oxygen polar bonds. As a result, carbon feels a bit electron deficient compared to oxygen. and that is why the cleavage of carbon oxygen bond is facilitated. In second step, the alkoxide is protonated with water to generate a neutral product with two functional group on adjacent carbons. The common nucleophiles that open the epoxide ring include hydroxide or alkoxide or cyanide or ammonia. With these strong nucleophiles, the reaction occurs by SN2 mechanism. The nucleophile opens the epoxide ring by attacking the ring from below, resulting in the formation of anti-product. Now, what is the meaning of this anti-product? We will discuss it with the help of an example. I told you earlier also that in a planar ring, attack can take place from both sides, that is from upper side as well as from lower side. Anti-attack means that first attack is taking place from this side, the other attack will take place from the other side. We will discuss it with the help of example in the later slides also. In case of unsymmetrical oxygenanes, the nucleophile attacks at less substituted carbon atom. Now, what is the meaning of this? We have here in this particular oxygene, this carbon is attached to 2-methyl group, whereas this carbon is attached to 2 hydrogens. You already know that when we have bulky group at the carbon, then this is a more, we will say, strained carbon or hindered carbon. Now, in case of unsymmetrical oxygenanes, the nucleophile attacks at the less hindered or less substituted carbon. Question arises, why? Why this nucleophile is attacking at this carbon and not at this carbon? The answer comes from within actually, because we know that this is an example of SN2 type of mechanism in which attack of nucleophile takes place from one side and then the cleaving group goes from the other side simultaneously. So, this is a hindered position, whereas this carbon can easily get the attack from the nucleophile. Let us now consider the stereochemical consequences of the reaction of 1,2-epoxy cyclohexane with methoxide ion. See, here we have, in this case, this is 1,2-epoxy cyclohexane. When it is treated with sodium methoxide in water, then it undergoes ring opening and there is formation of these two products. But if you look at them, you will find that both of them are almost similar. What is the difference between the two? That is, they rotate the plane of plane polarized light in different way, and that is why they are called enantiomers. Nucleophilic attack of methoxide occurs from the back side at either of the two carbon oxygen bond. The reason is both the ends are similarly substituted. Since attack at either side occurs with equal probability, an equal amount of two enantiomers are formed, which result in the formation of a racemic mixture. Here again we are showing the anti-attack on 1,2-epoxy cyclohexane. You can see here that this is 1,2-epoxy cyclohexane. The methoxide nucleophile can attack this carbon and generates this product. If the methoxide is attacking the other carbon, there is formation of product B. If you compare A and B, the only difference between them are that they rotate the plane of plane polarized light in opposite direction, or you can say that they are mirror image isomers. And this is possible because if you look at 1,2-epoxy cyclohexane, this is a symmetrical oxyrane actually, and attack can take place either at this side or at this side also. Now, when achiral reactant yield a product with stereogenic center, the product must be achiral, which can be either meso or a racemic mixture. In this reaction, optically inactive starting materials give optically inactive products. I will elaborate upon this point with the help of this example. You can see here this 1,2-epoxy cyclohexane is achiral. Similarly, methoxide is achiral. When there is no optical activity, how come we can get the optically active molecules here? And if we are getting in the form of racemic mixture or meso compound. In this particular case, we are getting equal amounts of dextro and levorotatory enantiomers, and that is why we say that we are getting here racemic mixture. Here this is an example actually where the reaction of isobutylene oxide and unsymmetrical oxirane is shown with sodium ethoxide in ethanol, and what actually you will find here is that the yield formed in this product is about 83%, that is the reaction is following SN2 mechanism almost completely. The mechanism of base catalyzed ring opening follows bimolecular nucleophilic substitution. The nucleophile attacks the less substituted primary carbon of the epoxide. We have discussed it earlier also. I am repeating once again that this position is a less substituted position at which the nucleophile is attacking. In the second step, the alkoxide abstracts the hydrogen or proton from the ethanol. As a result, the product is formed. Now we will discuss the reaction of epoxide in acid medium. Acids like HZ that can contain a nucleophile Z also open epoxide ring by a two-step sequence. Acids which can be used are either HCl, HBr or HI, as well as water or alcohol in acidic medium also can be used for this purpose. Here this is an epoxide. The difference, if you can compare from the earlier slides, is that the first attack in case of acid catalyzed ring opening of epoxides is the attack of lone pair of electron on oxygen on the hydrogen, and there is formation of protonated epoxide. This protonated epoxide then is attacked by the nucleophile on either of the two carbons. This is ethylene oxide. When treated upon with HBr, you can see that it gives bromoethanol. This is 1,2-epoxy cyclohexane, and when it is treated with water in presence of acid, there is formation of enantiomeric 1,2-dihydroxy cyclohexane. Actually, we get equal amount of the two enantiomers, so the product formed is the racemic mixture. Well, we will now discuss the reaction of 2,2-dimethyl oxirane, which is an unsymmetrical oxirane with acid. Here first step is same, that is the protonation at this oxygen of oxirane, and there is formation of protonated oxirane. Now in the second step, the nucleophile can attack either of the two carbons. If it attacks this carbon, then transition state B is formed. If nucleophile attacks position this carbon, then the transition state A is formed. Now if we compare the stability of these two transition state, we find that this transition state is more stable. The reason is that here the carbon, this carbon is not that electron deficient because of the electron release of two methyl groups. As a result, nucleophile preferentially attacks this carbon, or we will say more substituted carbon in case of acid catalyzed ring opening of epoxides. And the next step obviously is the formation of the addition product. Now we will discuss with the help of example almost the same reaction, in which a reaction of 2,2-dimethyl oxirane with methanol is done in acidic medium, and the product formed is 2-methoxy, 2-methyl, 1-propanol in very good yield of up to 76%. Here you can see that this carbon is a more substituted carbon, and that is why the attack of nucleophile, that is methoxy group, takes place at this carbon, and that is why the product formed. Now we will discuss the mechanism of acid catalyzed ring opening of an oxirane. Mechanism of acid catalyzed ring opening of an oxirane involves actually two steps. The first step is the protonation, and the second step is the attack of nucleophile at more substituted carbon, formation of the product this way. We will now consolidate the reaction of epoxide in presence of base as well as in presence of acid. We have seen already that ring opening of epoxide with either a strong nucleophile or an acid is regioselective, that is, one constitutional isomer is the major or exclusive product. And the second important point here is that the site selectivity of these two reactions is exactly opposite. We will discuss this thing with the help of the example here. You can see if we are using a strong base, that means the ring opening in presence of base, then the product formed is exclusively this, whereas in presence of acid the product is different. So, we can say that with a strong nucleophile attacks at less substituted carbon, whereas with an acid the nucleophile attacks at a more substituted carbon. Now, we will discuss some of the reactions of ethylene oxide or epoxides with Grignard reagent. In these reactions, actually primary alcohols are formed. Here you can see this is ethylene oxide, this reacts with alkyl magnesium halide, the Grignard reagent, and there is formation of this ring opening takes place, followed by the hydrolysis to get the alcohol. You can see here this is the alkoxy magnesium bromide formed by the attack of Grignard reagent on ethylene oxide, and then upon hydrolysis it forms the primary alcohol. Organometallic compound like lithium dialkyl cuprate can also react with epoxides, and finally the product formed is alcohol. Now, what actually are lithium dialkyl cuprates? They are organo-copper compound prepared by the reaction of alkyl lithium and cuprous chloride, and second step is the reaction of alkyl lithium with another molecule of lithium alkyl to give lithium dialkyl cuprate. Then alkyl lithium can also react with cuprous cyanide to give higher order organocuprates. In case of reaction of epoxide with lithium dialkyl cuprate, primary alcohols are formed. In this particular example, methyl cyclopentyl epoxide is treated upon with lithium dialkyl cuprate. You can see here that this is a cyclopentyl group with an epoxide having a methyl substitution. Now, when reaction takes place at this epoxide, the product formed is 2 ethyl, 1 methyl, 1 cyclopentanol, a primary alcohol. But you can see we have written here 1s and 2s also. This actually shows that in this molecule we have 2 chiral centers at these two positions, at position 1 and at position 2. Now, here first step is the attack of alkyl carbanion, the CH3CH2, that is ethyl carbanion attacks the less substituted carbon of epoxide, and there is ring opening and alkoxy lithium complex is formed, which upon hydrolysis forms this primary alcohol. So, this kind of reactions actually are used for the preparation of different types of molecules which have diverse uses in organic chemistry. We will now summarize today's lecture, in which we have discussed, actually we have introduced what exactly are epoxides. Then we have discussed the nomenclature of epoxides. They can be named either as oxiranes, they can either be named as epoxides, or they can also be named as alkene oxides. Then we have discussed the preparation of epoxide from alkenes. We have discussed their preparation from diols also, and we have discussed the preparation from halohydrins. We have discussed the reactions of epoxides in detail, and in which we have discussed the two reactions especially, that is base catalyzed ring opening reaction and acid catalyzed ring opening reaction which takes place on epoxides. We have also discussed the reaction with organometallic compounds in case of these epoxides. We have now completed all the episodes of ethers and epoxides. In the earlier three episodes, we have discussed the preparation of ethers, we have discussed their different physical and chemical properties. We have also discussed epoxides in detail, how the ring opening takes place and under what conditions the ring opening takes place in what direction. We have not discussed a very important, very interesting side of epoxide. Actually, they are called crown ethers, and these crown ethers find use in organic chemistry in phase transfer catalysis. We will actually not discuss it here because it is not to be discussed at this level, but I think you will find it in a number of books, and maybe in higher classes you will come through this topic also. Apart from that, all the ethers and epoxides find very good usage as solvent in a number of reactions which we undertake during our research or during our